these are notes on sort of the overarching principles of the carbon time units that we're going to be doing this year. So some of our units come from a curriculum called Carbon Time, which essentially traces the carbon that's both in your bodies and in the atmosphere. And we'll talk a little later about the carbon cycle. So a lot of you are familiar with the water cycle. There's also a carbon cycle and how carbon cycles both through our bodies and through other organisms and through our environment. And understanding that is really critical to understanding, first of all, what we need and how our bodies work, but then also a lot of kind of the environmental issues that we face right now have to do with carbon in our atmosphere, as you know, through carbon dioxide. So this can be found in your book on pages 348 and 349. If you keep reading to page 350, it also talks about endothermic and exothermic reactions, which we will learn in this unit, but I'm going to give you a little more background because I think as a biology book it skips over a little of the chemistry, and I think having that chemistry will make the concepts a little easier to understand. So we have 3 guiding questions that we're going to keep asking throughout the year. And the first one is the movement question. Where are the atoms moving? And specifically, we're going to talk a lot about carbon. But when we're talking about atoms, and for some of you this is going to be review, others of you this is going to be very necessary review, as in you know you were supposed to learn it but didn't, and still more of you may not have actually learned this yet. So atoms are something that's found on the periodic table. So if you look at a periodic table, and if you don't have one, simply Google periodic table and take a look. Something that's found on the periodic table is an atom. So if you have one particle of, say, oxygen, that is an atom of oxygen. Water, you'll notice, is not found on the periodic table, so it's not an atom. It's a combination of atoms. Carbon dioxide is not found on the periodic table, so that's clearly not an atom. It, again, is a combination of atoms. And in chemistry, we would say that an atom is the smallest unique particle of matter. So atoms are made up of smaller particles, electrons, neutrons, and protons, as hopefully you remember. But those particles are not unique to matter. And what I mean by that is a proton of carbon is exactly the same as a proton of hydrogen. An electron of sodium is exactly the same as an electron of nitrogen. But an atom of nitrogen is absolutely different and has different properties and interacts differently in the world or in the universe than an atom of oxygen. So the atom is the smallest unique particle of matter. And one of the things we always need to ask, whether we're studying biology or chemistry, is where are the atoms moving? Where are they going? Or where are they coming from? So then the next question we're going to ask is the carbon question. Remember these units that we do through this curriculum called Carbon Time, and it's not going to be every unit we do, but there are some really good units in here, is what is happening to the carbon atoms specifically. Okay? And finally, the energy question. What is happening to the chemical energy? And I want to emphasize here, the word chemical, because there's a lot of energy. And you learned last year about potential and kinetic energy. We're going to learn this year about chemical energy. And so, for example, you know if I roll a ball off a table, that ball, when it was on the table, had potential energy because it was above the ground. As it fell, it lost potential energy compared to the ground, and it gained kinetic energy because it sped up. So hopefully you remember those terms. I believe those are in your book slightly, maybe a few pages after the pages from this lecture. So if you don't remember kinetic and potential, you might want to kind of go back and look at those again. But here we're going to be talking about chemical energy. And chemical energy has to do with the energy needed to hold groups of atoms together and to break them apart. And when we talk about endothermic and exothermic more specifically, we'll talk about why some reactions produce a lot of heat, whereas some reactions require a lot of heat that seems to go into the reaction. So then we also have some rules for energy and matter, okay? And these rules, the first one is atoms last forever. And that is true whether the atoms are part of solids, liquids, and or gases. Those are all made of atoms, and the atoms in those last forever. There is one exception to that rule, and that has to do with nuclear chemistry and nuclear reactions. And so in like nuclear fusion that you get inside the sun, you actually have, for example, 2 hydrogen atoms fusing, combining together to form a helium atom. And in nuclear fission that you find in nuclear power plants, you actually split atoms apart. And this has to do with an interaction between matter and energy. This is what I'm going to say about this for now. That's something you will learn in chemistry. You will do a unit on nuclear chemistry. As far as the reactions we see within our body or within the environment around us, not including the sun, these reactions don't happen in those arenas. So in our scope of biology, we're not going to worry about nuclear reactions. And then I would also say that the particles that make up the atoms are still there. It's just that instead of being 2 hydrogen atoms, it's 1 helium, but you still have the same number of protons and the same number of neutrons. And if nuclear chemistry is something that interests you, you're welcome to chat with me about it at some point. So atoms can also be rearranged to make new substances. So if you have CO2, and again, for those of you who don't need a review, that's fine, but for those of you who do, remember the 2 here refers back to the oxygen. So the 2 is called a subscript because it's below the line. I've seen some people writing their 2's up here. Okay, it's not a squared sign. So let's, I don't know why I don't have an eraser on this. Okay, well, let's cross it out then. The 2 goes below the line. It's called a subscript. There are times when you use superscripts. Those are up here. I don't know that we're going to use them so much in biology, but you absolutely will use them in chemistry. So it's good to understand how to write these now. And I can show you, like on Microsoft Word, how to make a subscript too. And then it refers back to the previous atom. So this would be 1 carbon. We don't put any subscript in there if it's just 1. And then 2 oxygen. And that's carbon dioxide. And this prefix here, of course, di meaning 2. But then if you have C and just O, so you get rid of one of these O's and it, you now have this new thing, that's carbon monoxide. Mono meaning 1. And you'll notice there's no subscript anymore. So as we rearrange atoms, we make completely new substances. And both of these, carbon dioxide and carbon monoxide, are gases at room temperature. But carbon dioxide is, it's produced really naturally in our atmosphere. Carbon monoxide is one of the byproducts of gasoline exhaust. And it's incredibly deadly. So if you've ever heard of anybody dying from like carbon monoxide poisoning, a lot of times that's what it's from, in somebody's house, or maybe like a furnace is malfunctioning and it's pumping out carbon monoxide. Some people have carbon monoxide sensors in their houses because it's a colorless, odorless gas and you really don't know it's there until you become very sick from it. And then that rearranging of atoms is a chemical reaction. So we'll talk a little bit about physical changes and chemical changes. But if atoms are rearranged, that is a chemical reaction. So, for example, if water boils, the H2Os are not actually rearranged. They're still bonded together as hydrogens and oxygens. And we'll talk a little bit more about what that means to be bonded and the energy that's there. There is a review of ionic and covalent bonds. I think again, a couple pages after the pages that I just referred to at the beginning of this. One thing I would say though is they say that ionic bonds have less energy, or are weaker, I think, than covalent bonds, and that is absolutely not true. Ionic bonds are in fact stronger, and the way they phrase it is incorrect phrasing. So it's a decent overview of ionic and covalent bonds, but just kind of keep that in mind. And then finally, energy lasts forever. And there is an energy transfer in chemical reactions. So either energy goes into the reaction or energy comes out of the reaction. There's a net flow. And again, when we talk about endothermic and exothermic in more detail, we're going to really look at what this energy transfer looks like, where it comes from, why there's a net flow, meaning why energy overall goes in or overall comes out. Because there's actually energy needed at each part of a chemical reaction. There's energy that's needed and there's energy that's released. And so we'll talk about what that means and how that looks in chemical reactions. And in fact, you have that energy transfer in physical changes too. So again, go back to the boiling water. You obviously need energy in order to make the water boil. One last little caveat here, and that goes back to what I was talking about, atoms last forever, and I was saying there's a bit of an exception in nuclear reactions, same with energy. So the reason that we can essentially get energy from nuclear fission is because there's actually a transfer of matter into energy, and that is through the famous Einstein equation E equals mc squared, which is energy. Here, we can even write that out. Let's write that out. So E is energy equals m, which is mass, times c, which is the speed of light, squared. And as you know, the speed of light is really, really big. So that number squared is really, really big, meaning you only need a little bit of mass multiplied by the speed of light squared to get a ton of energy out. And that's what that equation means. And finally, I want to give you kind of scales of measurement so that we all know what we're talking about. In biology, we talk about 4 different scales. I would say in chemistry too, but chemistry tends to stick more in the atomic molecular. So the small, actually, let's start here. Let's start with the macroscopic. Macroscopic essentially means what we can see. Okay, and macroscopic tends to be in this green region here, and here is 1 meter. Okay, so that would be 10 to the 0. So this is a meter. Okay, and then if you know, like here would be a decimeter, that's 1/10 of a meter. A centimeter is right here. A lot of you guys are familiar with centimeters. Put in a little cm here. That's 1/100th of a meter. Or the reverse of looking at that is, so you understand that 10 to the negative 2 is 1/100th. Another way of saying that is there's 100 centimeters, cent meaning 100, that's why I talk about 100 cents in a dollar. There's 100 centimeters in 1 meter. Or each centimeter is 1/100th of a meter. And then we get millimeters. 1/1000th of a meter, or 1,000 millimeters, is 1 meter. So a lot of you guys have learned the macroscopic scale. You might know that this would be a decameter, this would be what's called a hectometer, and you can do this with liters too, or grams, and then kilometers. So a lot of us at some point kind of memorized from here to here. The scale below the macroscopic, below what we can see, is called the microscopic. And those are the things that we can see generally with microscopes. And there are names, just like we have centimeter, decimeter, hectometer, all in here. There are names for all of these 1/10 into intervals here, but we don't really use them. We go in chunks of 3. So 3 chunks down, or 1/1000th of a millimeter, or 1/1,000,000th of a meter, is called a micrometer. So that's 1/1,000,000th of a meter, or there are 1,000,000 micrometers in 1 meter. So this is our, from here about to here, this is our microscopic scale. And then we have our atomic molecular scale, okay? And that is the, that's the scale of atoms and molecules. And we don't have tools powerful enough to really see these. We can kind of map their surfaces, but we don't have any tool powerful enough to say, see a carbon atom and see the protons and see the neutrons. As some of you may remember, atoms are actually mostly empty space. And so you'd think if we had this tool, we could actually see the nucleus inside, and we just don't have that tool. And so 1,000 units down from a micrometer is a nanometer. So that's right here. And so that is, let's say, that's 1/1000th of a micrometer, 1/1,000,000th of a millimeter, so 1/1,000,000,000th of a meter, or 1 billion nanometers is a meter. And that's what we call the atomic molecular scale. And then on the flip side of these, we have what we call large scale. Okay, and it is exactly what it sounds like. The large scale is larger things than that macroscopic scale. So for example, the size of a galaxy would be considered large scale. The distance from even like here to the sun or across a solar system, that would be considered large scale. So the small end of large scale is at the end of that scale that a lot of us have memorized at the kilometer. And then in fact, if you go out 1, 2, 3, so this would be 10 to the 6th, if you're using these like football field lines. This is called a megameter. M-E-G-A. And I'm pointing that out to you. Now, in this it says larger. Anything larger than that is also large scale. But I'm pointing that out to you because a lot of people confuse mega and milli, not in confusing what it is, but when we're abbreviating, when we use a capital M, we mean mega. And we mean 1,000 kilometers or 1,000,000 meters. When we use a lowercase m, we're meaning milli. So just know that there is an actual difference if you use a capital M versus a lowercase m. And we're going to talk about these 4 scales and what they look like and interact with all of them within the scope of biology. So please, if you have any questions, you can add them to the comment section of YouTube or write them down so that you can ask them in class. Have a good night.